Hi. So this time I would like to solve some problem, a concrete problem for the wave equation in three-dimensional space, just to see how these formulas work. So our equation is u t minus Laplacian with respect to x u equal 0. U equals u of xt, x in R3. Initial condition. Let me first remind the formula. U for t equals 0 equals f of x, ut for t equals 0 equals g of x. And the formula which I derived last time, the Kirchhoff formula, is the following. U of xt equals 1 over 4 pi t, integral for y in the sphere, the point center x with radius t, g of y ds y plus d dt 1 over 4 pi t, integral y in s of x with radius t, f of y dsy. So this is the formula, and let us consider the following particular case of this problem. Again, u t minus u x minus delta u equals 0. U for t equal 0 equals 0. Ut for t equals 0 is the following function. Is 1 if module x less than r, and 0 if module x no less or equal more than r. So this is our problem. No, I took just half of initial conditions, and voila. So how to find a solution of this problem? In if f equals 0, that only the first integral remains. The second is 0 because f is 0. So u of xt equals 1 over 4 pi t, integral over the sphere, y in s of xt, g of y dy. And g of y equals g of module y equals 1 module y less or equal than r, 0 module y more than r. And here we can see different cases. So on one hand we have this ball with center at the point O of radius r. Here this function g equal 1, outside is 0. And the second is the sphere, with integration goes over the sphere with center x and radius t. So the sphere can be situated in different locations. So we have the following cases. The sphere can be here. It can be entirely inside the sphere. Let me draw it. Okay, let's take this. So the sphere can be like this. So module x is of course less than r, and module x plus t, this radius t. So it's the case module x plus t less than r. So the sphere is inside. The sphere can be outside. So this is our sphere of radius r, a ball of radius r, and the sphere can be like this. Yes? So the center is somewhere here. It is module x, and module x minus t, one moment, module x plus t, module x, it is module x plus t, it is module x minus t. No, t is positive, but they both are in more than r. And there is the case when these two spheres have only partial intersections. So in this case, module x plus t more than r, module x minus t less than r. Yeah? So this module x. Module x plus t more than r, module x minus t less than r. So we have this configuration. So now let us look here. What happens in this case? In this case, if module x, if we have a small sphere, it happens then when t is sufficiently small and module x is sufficiently small. In this case, we have all this sphere is inside the ball where the function g is 1. So here u of xt equals 1 over 4 pi t times integral over the sphere of 1. So it is the area of the sphere. Area of S with center x and radius t equals 1 over 4 pi t times, if the area of the sphere of radius t is 4 pi t square. So in this case we have just t. Yeah? It is one situation. Other situation is in this case. In this case, all the sphere which is of radius t, where this integration is done, is outside of this sphere of radius r. So everywhere here, the function g is 0. So in this case, u of xt equal 0. Let me divide these two cases. And the last is this case. In this case, it will be something intermediate. So in this case, the problem boils down to find the area of this part of the sphere of radius t, which is inside our ball of radius r, where the function is 1. G is functional is 1. So it is a geometrical problem, interesting geometrical problem, which we have to solve. So let us do it. So we have a sphere, it is the point O, it is point A, OA equals R. It is a sphere of radius R. Here we have the sphere of radius T. But first of all, its center is point B. Is OB equals module X. Yeah. And now we want to have this point C, intersection point. So let us find it. It is OB is module X minus T. So OC equals module X minus module X minus T. Okay, and we are interested, one more, it is a cross-section of two spheres, intersection spheres by a plane. Imagine that they are spheres. Now we have need the following thing. Let's consider this point which is called D. We join these two points of intersection and this point D. And OD equals, let me denote it by Z. And it is important thing, the most important thing. So let me make a step aside. And remind you about one great theorem, which is called Archimedes' theorem. It says the following. Suppose we have a sphere. Yes? And the sphere has, say, radius r. And suppose we have a plane which intersects this sphere, say at the point whose distance, say, let me call, it it is C, it is D. I take this fragment of this. And we consider the area of this part of the sphere, which is to the left of the plane which is perpendicular to the line CD. Yes, this is point B. I refer to this picture. So let us recall, let us denote this area by S. And Archimedes' formula is the following. Area of S equals 4 pi, no, it is not R, it is T. Yes, because it's point B, this is T. 4 pi T square times CD divided by 2T. So what is this? This is the full area, and the formula says that the area of this part, no, let us call it spherical cap, is proportional to this segment CD. So the area, say, if you move this plane orthogonal to CD, then the area of S changes linearly. It is linear function of the distance CD. So for when this distance is 0, the area of course is 0. When distance equals 2t, the area is 4pi t square. And no, for intermediate values it's somewhere in between. So this is the Archimedes theorem which I am using. So here we have all the elements. We have only to find this distance between the points O and D. Now let us do it again. We have these two spheres. Let us denote this point A, B, C, D, say P. P. Let us draw this segment H, it's perpendicular. It is O. It is B. And draw this OP. OP and BP. This is R, this is T, yes, and this is Z. And OB is module X. Then by Pythagoras theorem we have Z square plus H square equals R square. In this right triangle, module X minus Z square plus H square equals T square. So we have the system of two equations, and we can eliminate here H, just subtract one from the other, and we have Z square plus H square minus module X minus Z square minus h square equals r square minus t square. Okay, I have to go here. So, z square plus h square minus module x square plus 2 module x z minus z square minus h square equals r square minus t square. Now here something is cancelled. This and this cancels, and we have 2 module x z equals module x square plus r square minus t square. So z equals module x square plus r square minus t square divided by 2 module x. Okay, I'm sorry, I have to finish this. So we found this segment OD, which is Z. Z is given by this, from these two triangles. Now we have to find CD. CD is found because OC is OB minus BC, OB is module X, and BC is T, and OD is Z, so CD equals Z minus module X plus T. So CD equals Z minus module X plus T. Okay. And now it is CD. And now by the Archimedes theorem, we have to find the area of this part of the sphere, of this center at the point B, and radius T, S, area of, no, S is not good, let us call it sigma, of sigma equals 4 pi T. 4 pi T, it is the area of all the sphere, times CD, it is this, divided by 2T. 2T is diameter of the sphere, equals CD is Z minus, so it is 2 pi Z minus module X plus T uh, 2 pi for T square, 2 pi T. Yes, so we found the area of this part. Okay, and now from this we find the solution. U of xt equals 1 over 4 pi t integral over s of x t g of y ds. Now g of y is, here it is 1, here it is 0, so it is exactly the area of this part equals 1 over 4 pi t times 2 pi t. One moment. No, it's okay. Times 2 pi t z minus module x plus t. Yes. No, this is, so we have to equals 1/2 z minus module x plus t. Yes, possibly. Where z is found by this formula. No, it was not very much transparent, but it is a little bit tricky because here we have different cases. So we have first our ball of radius r, and we have here the following cases. The point x can be inside this ball, say here, it is module x, and the radius, the time t, can be so small that all this sphere of radius t is still inside this ball. So it is case, the first case, so this means that module x plus t less than r. In this case, all this ball is inside our, all the sphere inside the ball. We have two opposite cases. We have this case, when the sphere is, it is x, no, module x, and it is t. So in this case, we have this r, this is t, so module x more than r plus t. In this case, our this sphere with center at x at radius t lies outside, completely outside the ball of radius r, where inside this ball g equals 1. We have also the case, this is the ball of radius r, and our sphere is completely outside in this way. So it is module x here, and it satisfies the following: module x minus t, I mean this point, less than minus r, or module x less than t minus r. Yes, it is this case. And we have the remaining case when this is our ball of radius r, this is our sphere, and in this case module x minus module x minus t, it is this point, more than minus r, module x minus t less than r, and module x plus t more than r. Yes? So to have this situation, we should have all these three inequalities. And it would be interesting to draw a diagram for all this. So we have here 4 different cases. Now, first of all, our solution, which is here, is found for this case, where we have some non-trivial intersection of this sphere and this ball. In this case, it is completely I'm sorry, let me repeat. I have to draw some diagram, so let me write here z equals module x square plus r square minus t square divided by 2 module x. Yes, it is and u equals this. So I can erase this. U of xt equals this. So let me erase this too. And so let us draw the diagram. Here is module x, and here is t. These 4 cases corresponds to 4 domains in this diagram. So this case, module x plus t less than r. It is here. It is r, r. it is domain, this domain, domain number 1. Domain number 2, module x more than r plus t. Module x more than r t plus r. It is this domain 2. Yes? What is this? Module x less than t minus r. It is this. Yes, and this is what remains. So our solution, which is here, after all it is not so complicated, holds here in the domain number 4. Now, what about solution in case 2 and 3? In this case, this sphere does not intersect the ball in this case. So this means that in the cases 2 and 3, we have u equals 0. And here, u equals 0. In case 1, here, it is here u equals t. So in case 1, u of xt equals 1 over 4 pi t times integral over s x t ds y, because here the function g is 1, so equals 1 over 4 pi t times area of s of xt. This area is 1 over 4 pi t times 4 pi t square equals t. So here u equals t. And here, you have this not very tricky, but some formula. I would like to consider here one case. What happens if x is 0? X is the origin. Yes? So then we have the following situation. You have x is in the origin, so for t less than r, all our sphere is inside this ball. So we are in domain 1 and u equal t. We are moving along this line. And then for t equal r, our sphere is the boundary of our ball. And then for t more than 1, it is like this. Yes? So this means that we are going along this line. So here u equals t, so it grows linearly. And here it becomes 0. So solution at the center looks like this. It grows linearly and then falls down and then it is 0. Okay. In fact, it is a good question. What happens if our point is at some other point? Then, if you have some generic point, not the center, then what will happen? This sphere will grow. At some moment, this sphere touches the surface of the ball. So until this moment, the solution grows linearly, and then it will become, so this means that we started here, then time is going on, and then we got in domain number 4. This is domain number 4, where we have non-trivial intersection. Then here we have this formula, and it is additional task, which I am not doing now, to prove that there is no jump. So solution, it was growing linearly, and then it becomes growing accordingly to this formula. But the important thing is that when it grows further, the area inside the ball decreases, and then at some moment it becomes 0 and remains 0. This means that we crossed this border and are in domain number 3, where u is identically 0. But it goes continuously. The only discontinuity is at the center. Similar things is when you start from outside of this ball. Our sphere is growing. So we start from 0, it was 0, 0, 0, then it touches this ball, and then it intersects this ball, and the solution is not 0. So this means that you start somewhere here for R large. So here we still do not reach the ball. Then we reach the ball, are inside it, but then we reach this situation when solution again becomes 0. So you see, it is a rather rich stock of interesting cases. No, okay, let us finish now and continue next time, which will be soon. For now, let's finish. Have a good time. Bye.